Okay, good afternoon. So we will continue with the duality, and some part is left. So we will try to finish that today. So recall that given an optimization problem like this, which is in the standard form now, we define the Lagrangian to be like this. So objective function and then lambda I times the inequality, mu I times the equality constraint. And here lambda I, nu I are called Lagrange multipliers. Okay, in other words, there is another name. They are also called dual variables. Okay, or Lagrange multiplier vectors. Okay, so we have seen this before. And then we have defined so-called dual function. So dual function is the infimum of the Lagrangian. So you have to solve this infimum problem. Okay, and then it depend. Then after solving this infimum problem, we are left with lambda and nu. If the Lagrangian is unbounded below, then the dual function takes on a negative infinity value. Okay, and the Lagrangian, this is an affine function of lambda and nu. So this is also we have seen before. G lambda nu is the infimum. So this is like convex because it's affine. Okay, so G lambda nu will be an affine because it's the infimum of a set of affine functions. Okay, so overall this will be guaranteed to be concave. Okay, so since we are talking about infimum, supremum of convex is convex, and infimum of convex functions is concave. So at least this is guaranteed. And concave is also good because negative of that will be convex. So that's a nice function to work with. And all this is true even when the original problem may not be a convex problem. Okay, so originally fi, hi, f naught may not be a convex function, but it turns out that G lambda nu is a concave. Okay, so this is the things we have seen before. Now the dual function yields a lower bound on the optimal value. This is also we have seen before for any lambda greater than or equal to 0 and nu. So this is always part of the formulation of the Lagrange multiplier. So what we have is G lambda nu is less than or equal to P star. This is the primal optimal. And this is something we have proved before. So we always have this. The dual function values are always less than or equal to the primal optimal values. And we have seen in examples where we have we are given a primal optimization problem, and then we can construct the Lagrangian, we can form the dual, and then we can check whether it's a dual function is concave or not. Okay, and then whether that inequality holds. The dual function values must be less than or equal to the primal. So all this we have done in the last class. This is another example again, and this is another example. We have done this. Okay, there is a connection. At some point we have studied conjugate functions, right? So conjugate functions were defined to be like this. Okay, if you can recall. So for a given function fx, the conjugate is defined to be like this. Now there is a relationship between the Lagrange dual and the conjugate function. That is what I'm going to explain now. So they are closely related. So consider a simple example like this. Then the Lagrangian for this is fx plus nu transpose x. Okay, and because there is only equality constraint, so we have only that term here. Then the dual function in this case is G nu, which is infimum of the Lagrangian over x. And yeah, so this is the part where we have to focus. So this is infimum of x and then fx plus this. Now this can be written as supremum of the minus of the inside term, right? So infimum of f of x is same thing as doing minus of supremum of minus of fx. Okay, so this is what we are assuming. This is what we are trying to do here. So infimum of this is negative of the supremum of the negative inside. Okay, so if we do this, then we immediately recognize that this thing can be related to the supremum thing here. Okay, so this is like supremum over x, the same thing here, and then in place of y, I have minus nu. Okay, so in place of y, I have minus nu, and then other things are the same. So this can be seen because this is a function of y here, right? So in place of y, I have now minus nu. So I can write this as f star of minus nu. Okay, minus this minus still here and this minus still here. So this is the way I can relate. So what it means is if I know the dual, of a given function, then obtaining the Lagrange dual can be done in this way. Okay, so if you know f star of a f, then it's easy now to construct the dual. Okay, for the standard cases we already know f star, so we just have to plug in the value like this. Okay, so this is how they are connected. So for example, if you see this example, then by using the conjugate function we can also write things quickly. So we know that the dual function g lambda nu is this, which is infimum of the Lagrangian. So this is the Lagrangian, objective plus lambda times inequality and then mu times the equality constraint. So this is the Lagrangian and we infimize over x. And if we infimize over x, so we take out the terms that are independent of x outside, and then the infimum is applied on the remaining terms here. Okay, so this is still the first term, and then if we look at this, right? So we have to put this in the form. So if we look into this term, which is infimum of f naught x plus a transpose lambda plus c transpose nu transpose x. So we use that trick. This is minus of supremum of minus, let us write this term first. So A transpose lambda plus C transpose nu transpose x minus F naught x. Right? Now this is like that Y transpose, right? So this is like the Y transpose form, Y transpose x minus F naught x, right? So this will be F naught, so this is minus F naught star, and in place of Y we have this, which is minus A transpose lambda plus C transpose nu, right? So this is what we have done here, and this is what we obtained here. So using the conjugate, so it's conjugate of F naught. Okay, so if we have a table of things where we conjugates are known for a well-known functions, then we can just substitute it to get the dual Lagrange dual. Same thing in this different example here. So here we write the Lagrangian, objective plus lambda times ax minus mu plus nu transpose, and then the equality constraint. Now the independent terms. Okay, so this is the same thing, right? Okay. Now look at this actually. Yeah. So in this case, the conjugate is known. So conjugate of this guy f naught x is this. Okay, so this is something, it is shown in the book if you see. Okay, maybe I have done this as an example as well, I don't remember. So conjugate of the norm is well defined, and it is found to be like this. Now if we write the dual function, then it will be like this. Okay, so at this place I just have to like substitute it by the conjugate. Okay, so yeah, lambda and nu, right? No, I think this term is not there, right? Because this is just equality constraint, so it is enough to have just this minus yeah, so this is like ax minus b, and then mu transpose, and then yeah, and then plus f naught x. Okay, so this is the Lagrangian mu and x, and then if we have to infimize this, Okay, so this will be infimum. So if I write this as nu, then this is infimum over x, and then what is left, right? So what is left is f naught x plus nu transpose ax, and what is outside is minus nu transpose b. Okay, so this guy here, and then yeah, so the infimum of this will be I think there is some mistake here. Okay, so let us forget this. So I'm trying to derive it now. Okay. Okay, so here I will write this in that form, right? So this is like minus supremum of x and minus nu transpose a x plus f naught x, okay, minus nu transpose b. We have to put this in this form, right? So we should write this as a transpose nu and then transpose x. Okay, so this is like minus supremum over x, a transpose nu transpose x. Okay, and let us put minus also inside, and minus f naught x. Now this plays the role of y that we are looking for. So now we can write this as minus f naught star plus a transpose nu. Okay, and this is what is written here, and minus mu transpose b or b transpose mu is the same thing, and it goes here. Okay, and this is coming from here. Okay, so but this guy is known to us. So f naught star x for the norm, the dual of the norm is found to be like this. So this is what we have substituted here. So dual of this, in place of x, we have now minus a transpose nu. Okay, so we put those. So it will be 0 whenever this y is less than or equal to 1, which is this case. So 0 plus this term. So we will be left with this, and remaining will be infinity. Okay. Yeah. So this and then negative is there, right? So that's why overall it will become minus infinity. Okay. Okay. So this is the this is how the conjugates can be used. So what we learned about conjugate is an important thing that can be used in duality, and duality we know is a technique to solve constraint problems, right? Constraint optimization problems like this. Okay, now we're moving ahead. So now let us look into the so-called dual problem. I have not yet defined dual problem. What I have defined is a Lagrangian and the dual function, but I have not said what is the dual optimization problem. Okay, and the hint I already gave you before. So let us say everything is as assumed. So the Lagrange multipliers are there, and lambda in a Lagrange multiplier is always greater than or equal to 0. So Lagrange dual gives us the lower bound. So this is what we know. G lambda nu is less than or equal to p star. So this is something we started with in this lecture. So this is the lower bound. Now naturally we know that, so this is the p star is somewhere here, let us say, and G lambda nu for some nu is here. Now, as I motivated in the previous classes, my goal is to just approach this via this way. Primal problems go like this because they are minimized. Okay, so they are like f naught x you're supposed to minimize, and here I can also go this way. So naturally the dual problem is like maximize G lambda nu. Okay, so that will be the dual problem. So dual problem is maximize your dual function, and subject to what is the constraint. Its only constraint was on lambda, which is greater than or equal to 0. Mu goes with equality, so it doesn't change the equalities, but lambda greater than or equal to 0 was necessary for us, so that the inequality remains inequality, right? So this is called the Lagrange dual problem. Okay, so this is the Lagrange dual problem, and the original operation problem is called the primal problem. So the pair lambda nu, if lambda greater than or equal to 0, and I mean these are the assumptions we are making in the sense that that we will define what is dual optimal. Okay, so we are assuming that it takes some value which is not infinity, minus infinity. So it should be like lower bounded and so on. Okay, that's why then we can talk about at least getting some maximized value, right? If it is always minus infinity, then we get minus infinity and it's like absurd things, right? So we make an additional assumption that it takes some finite value. Well, it can go up to infinity. That's another way, but we are expecting that it has something other than minus infinity to make it a non-trivial problem. Now, optimal solution denoted by, just like we had optimal solution denoted by X star, optimal primal. Here we have optimal dual. Okay, so then we use star. Okay, so these are called dual optimal. Okay, so now optimization problem above is a convex optimization problem. Why is that? Because this is convex. Okay, so this is convex, and we can put this in standard form in the sense that minus lambda is less than equal to 0 by multiplying by minus 1 both sides. So overall, this is a standard convex optimization problem because the objective is convex, and these inequalities, I can write this in this form. Okay, less than equal to 0 form. It's like a fine form. So it can be solved by a convex optimization problem actually. Okay. So, and this is like a linear, okay? So it's like linear. So linear functions are both convex and concave. Regardless of minus plus, it doesn't matter, right? So this inequality constraint function is also convex, okay? So objective is convex, inequality constraint function is convex. So the problem is known to be a convex optimization problem, and this is what we have. And this is regardless of whether the primal problem was convex or not. So that's very important, right? Primal problem may be non-convex, so it's very hard to find solutions there. Okay, and then you go to the dual, and then everything is nice. The problem is convex. You can use gradient method, and you are guaranteed to converge. Okay, so these are the good things about the dual problem. So just like a primal, let us say that D star denotes the optimal value of the Lagrange dual problem. Then we always have this, because we always have this lambda nu is always less than equal to P star. And this is for all lambda nu. So in particular, also for lambda star, for which it assumes the maximum, that should also be less than equal to P star, because that is just one specific value of that. So this is nothing but D star according to our definition. This is less than equal to P star. That is something we know. And this is called weak duality, where you have the dual is less than equal to primal. So primal is somewhere here, and in the dual we solve it from this way. And let us say you may hit up to here at some point, and you are not able to. Maximum value of G lambda nu is this. Okay. So then you have a strict inequality. In this case, D star is less than P star. But it may happen that D star hits P star. Okay, and in that case, we will call it a strong duality. So if you have this one, where you cannot guarantee the equality, so where you cannot guarantee the equality, but at best you can say that it may be less also. Okay, then you will claim that this is like weak duality, because your assumptions are weak. You are allowing also less than, right? And then if it is so, then I can take a difference, and then this will be P star minus D star will be something positive, okay, or non-negative. If it is equal, then it will be 0. So this is called the duality gap. So what is the gap between your dual optimal and the primal optimal? Okay. So if D star is equal to P star, then we say that it's strong duality holds. Okay. The strong duality does not hold in general. Okay. So you should remember this. Strong duality is not always given. Okay. But if the original problem is convex, then we usually have strong duality. If the original problem is convex, then you are guaranteed to have strong duality. In other words, the dual optimal that you will get will be equal to the primal optimal. Okay. But it's not the if and only if case. There may be non-convex problem as well. Your original problem may be non-convex, but still the strong duality may hold. Okay, what this is trying to say is that if it is convex, then it is guaranteed. If it is non-convex, it may or may not imply strong duality. Okay, non-convex, it may or may not. Okay, so but there are certain conditions if those are satisfied, then we can guarantee strong duality. Okay, so one of those conditions is so-called Slater condition. Okay, so if the original problem is convex, strong duality holds. Okay, so one way is like if you indeed want to solve your problem still via dual, even though your primal is optimal, primal is convex. Why would you do that, right? So one question is, why would you convert your problem to dual now? Already your primal was convex. Well, there are cases where even though it may be convex, it will still make sense to go to dual, because it may happen that the dual variables lambda and nu are low dimensional. Okay, remember that in primal you are solving over x. In the dual, your gradient method will use variables lambda and nu. If it so happens that your primal variable lives in a very high dimensional space, let us say million or something, billion, something like that. And if it so happens that my dual variables are nice, they just sit in this. Okay, let us say 200. I would prefer to go by this way, because the gradient methods, the memory requirements that I will need are less here. Okay, compared to the memory requirements. If I run a gradient method here, then I will produce x old, x new, and then I have to put in those in the memory, and this will consume a lot of memory. But if I go here, I will be only, at most I will be using like 200 dimensional space. So there is still something that makes sense sometimes when you go from primal to dual. It is also about memory sometimes. Okay, it may happen that you are in the situation is reversed. Okay, it may happen that x was in 100 dimensional space and your dual variables are going in millions. Then it's not a good idea to go to dual. So even though your original problem may be convex, it may still make sense to go to dual if you want to save on memory requirement and so on. So dual is still a good thing. Okay, in some cases. So, but in general, if you don't know about convexity, then the question is, are there any conditions that I am going to check which will prove the strong duality? So there is one such condition called Slater condition. So it says that if you can find some x, one x, it's not saying all x, okay? It's just one x, okay? One is enough, one x. If you can find just one x in the domain, let us say by some way, hook or crook, so some way you can do trial and error, and you can produce one x by some guess, such that all your inequality constraints, all inequality constraints are strict inequality. Okay, in general, remember in the optimization problem, we are given less than equal to. But what we are saying is like if I can find an x such that for that x all the inequalities are strict inequality, okay, then it is called a Slater condition. Okay, and such a point x is called strictly feasible because it's satisfying the strict inequality. This is just a definition here, and this is called a Slater condition. So assume that the and here, like, okay, I should be a bit careful. I said in general, right? But I should say that it is usually have strong duality. Okay, I'm going to correct my error. So I said that when it is convex, then it is usually follows strong duality, but we need some additional condition here, which is a Slater condition here. Okay, sorry, I made an error here. So even if it is convex, it is still not always strong duality unless it satisfies additionally a Slater condition here. Okay, so this should be added furthermore. So assume that the primal is convex and Slater condition holds, then the strong duality holds. Okay, then strong duality holds. So there is still something needed apart from convexity, which is so-called Slater condition, and then it guarantees strong duality. Okay, so and let us say if so Slater condition can be reduced a little bit when some of the FIs are affine. Okay, so Slater condition when some fi's are affine, then so for affine you are like allowed to have you are allowed to have equality as well. So there is a slight refinement to the Slater condition. So it may happen that I'm supposed to minimize, let us say f naught x, and then let us say some of my constraints are, let us say x1 plus x2 is less than equal to 0, and then x1 square plus 2x1 x2 is less than equal to 0, something like that. Okay, so this is my f1x, this is my f2x. So what this is trying to say is that strict inequality may not be needed or not needed at all if you have affine. Okay, so if I have affine, it is still okay for that to be equal, but wherever you have non-affine functions, there it is enough to satisfy strict inequality there. Okay, so this is a further refinement of the Slater condition. If so, you will go ahead and look for only non-affine inequality constraint functions, and you have to get strict inequality only on non-affine. Okay, it is okay for affine ones to be less than or equal to 0. So this is a further refinement here for Slater condition here. Okay. Okay, so if we look into some examples, so remember this seems to be a convex. Okay, so this seems to be convex because the grad square of f naught x is identity, and this is like a positive definite. So by second order test, the f naught x is convex, and there is only equality constraint here. Okay, so I can write this as ax minus b equal to 0. So this is a equality constraint. So this is my, let us say I write this as a vector, right? So this is the vector functions h, and these are affine. So convex as well. Okay, so this is overall this is a convex problem. Okay, so this is a convex optimization problem because objective function is convex, equality constraint functions are convex. There are only equality constraint here. So this is a convex optimization problem. So first step is done. Now a convex problem may not always imply strong duality. So for this to satisfy strong duality, what we need additionally is that the inequality constraints are strict. But here there is no inequality constraint, right? So there is no inequality constraint to be satisfied. Well, so Slater condition holds by default. Okay, by default, the Slater condition holds because there is no inequality here anyway. So the only thing now you should be worried about is whether this problem is feasible or not. So there is a feasibility check going on here. So where if B should be in the range of A, so that this solution there is some feasible set. Okay, in other words, there is a solution X for this system. Then there is some domain over which I'm going to minimize. So these are just additional checks. If B is in the range of A, then the Slater condition just holds. Okay, because inequality constraint is not there. The only thing now we have to check is like, is everything feasible? That is a standard check for any optimization problem anyway. So B is in this, then prime P star must be equal to D star. It may also happen that the equality constraint is not satisfied. In that case, the its problem in that case, like basically we don't have like B is not in the range of H. It's the primal is like the feasible set is empty, and then the infimum of the empty set, right? So it's like it will be like minus infinity and so on. Okay, so and hence in that case we will also have the dual also to be minus infinity, because dual is always less than equal to primal. So if this guy already became minus infinity, then this has to be minus infinity as well. Okay, so hence the Slater condition is satisfied always for this example. Hence strong duality holds. So if you encounter problems like this, the first step is to see whether the convexity conditions are hold for the objective and the constraint functions, and then check whether there is inequality constraint. In this case, there was none, and then Slater condition holds, and then you are safe. What all this is saying is that it is safe to use duality and solve dual problem, and then the solution to that will be will be primal optimal as well. Okay. Okay. One may still ask, like, let us say I found optimal of the dual. Now, how do I get back to the primal optimal, right? So this question is still not, we don't know yet, right? Although we solve this, we can find the D star from here, which is G of lambda star nu star, but we don't know at which X star, right? Because originally someone gave you this problem to find X star, not lambda nu, because for their problem, X has a meaning, not lambda nu. Okay, so you have to know how to get back to X star, right? Okay, so we will come back to that. Okay, so let us see one more problem where regarding Slater condition. So this is QCQP, right? Quadratic constraint, quadratic program, right? So you remember this? Okay, so here, like the standard assumptions are there that comes with QCQP. So this P naught is strictly positive definite and PIs are semi-positive definite. So write the Slater condition in this case, right? So the Slater condition in this case will be what, right? So yeah, so in this case, what will be the Slater condition? Well, one thing we know is like this is convex and these guys are also convex due to the definitions of this PI being a positive definite, because this is semi-definite and this is strictly positive definite. So overall this is convex because grad square of f naught x is nothing but P naught, and this is positive definite. And similarly we can do this and the grad square fi x for I greater than equal to 1. These are PIs, and these are also given to be positive definite, semi-definite, but still fine. It's convex. Okay. So write the Slater condition, right? So this. So what is the Slater condition in this case, right? So well, we have to look. We have to go for the inequalities here. Okay, we have to look for the inequality and then make it strict, right? So we have to make this inequality strict, right? So in this case, I can write the strong duality holds if there exists an x, right? We have to find an x, feasible x, such that half of x transpose pix plus qi transpose x plus ri is less than 0, right? So I equal to 1 to m. X is fixed, but it should satisfy a strict inequality for all m, right? So this is the Slater condition that we know. And writing the Lagrange and the dual, I will leave it. Okay, this is something we have done before. And then the dual problem also, I leave this. You can also refer back to the book. Okay, so this is a solved example. Here is the page number. Okay, so the main thing here I wanted to discuss was Slater condition. Okay, one more problem could be this. Now, what this is saying, this example is an example where non-convex also can actually satisfy strong duality. Okay, so they can also satisfy strong duality. So what from this problem, I'm not going into detail of this, but if I write a dual of this and if I solve that, then the solution that I will get for the dual will be also will match the optimal dual will match the optimal primal. Okay, so this is just an example to refer to you. Now you may go ahead and like try to form a dual and solve that. Okay, so you may go ahead and do that, and you will find that the D star is equal to P star, although this is not a convex problem. Okay, because this is not positive definite. Okay, so this is grad square f naught in this case is A, and this is not positive definite. Okay, so this is a non-convex problem. Okay, but still you will find that D star is equal to P star. So this is a counter example, okay? In this case that, so where even with non-convex, I may still hit a strong duality. So strong duality holds for any optimization problem fail with, so this is like another generalization of the, you can say that this is a slight generalization. So let us see what it is trying to say. Strong duality holds for any optimization problem with quadratic objective and one quadratic inequality constraint, provided the Slater condition holds. Okay, that is, there is an X feasible such that the quadratic inequality. So this is exactly that case. So what this this strong duality, what this is trying to say is a slight generalization in the sense that my problem is not really convex because my objective is not convex, and but it is a quadratic. So this is a quadratic objective, and I have one quadratic inequality. So for those problems as well, like there is like a, one can like prove this in general. So for those problems as well, will of this template form will satisfy strong duality, provided that it has one quadratic inequality. Okay, it has one quadratic inequality and it satisfies the Slater in the sense that I can find one X for which this is like strictly less than equal to one, less than one. Then in that case also, even though it's non-convex, it will still satisfy the Slater condition. Okay, so there are generalizations of Slater condition. Okay, I am not going into more detail of this. So there are more generalizations of Slater conditions. Okay, so there is a definition of so-called certificate of proof. So if there exists a dual feasible point, let us say lambda nu, then we know this always. So primal is always greater than optimal is greater than equal to this. So here we say that lambda nu provides a proof or certificate that the above condition holds. So what this is trying to say is like, if I can get some lambda in nu, okay, then it will satisfy this inequality, and here lambda and nu serves as a certificate. Okay, it serves as a certificate that the above condition holds. Now how, I mean, this can be used in some sense. How, right? So here this inequality, I can write this as P star minus P star is less than equal to minus G lambda nu. And what I know also is that F naught X is equal to F naught X. And then I add these. Okay, so if I add this, then I get F naught X minus P star is less than equal to F naught X minus G lambda nu. Okay, so this is the proof of this. So what does it say, right? So what it is trying to say is like the F naught X and the difference from the primal optimal value is bounded by this. Okay, so it's bounded by this. In other words, I could have taken this as some epsilon value, let us say. Then I am my closeness from the P star can be found from here. Okay, so this is what it's trying to say. So how close my primal is to the primal my function value is, because maybe I'm using some iterative algorithm. Okay, so at some point I get F naught X K and then minus P star. So this is bounded by F naught Xk and minus G lambda nu. Okay, so for some lambda nu, let us say I produce, then I mean this lambda nu I can use as a test. Okay, so let us say I put some random lambda in nu, and then I will check the difference. And if it, let us say for some reason, if it becomes very small, let us say 10 to the minus 10. Okay, in practice so I tested on some lambda nu and I took the difference. And if I found it to be 10 to the minus 10, then what does it tell me? It tells me that I am actually 10 to the minus 10 close to already the primal optimal. Okay, so it can also give me a way to stop maybe. Okay, so I will say that, okay, I think I'm close to this. The good thing about this is like it's giving me the difference directly to the primal optimal, right? In general, so what people may do in general, because in iterative, because you have no knowledge of P star. So what people may do in general would be something like this. So in the new function value that I got minus the old function value that I got, if I did not make much progress in minimizing, let us say it was like very close to minus 14, like almost it seems like almost I'm making no progress, then I will stop. Okay, so this is something people may try. But remember that this is a bit dangerous, because here you don't know whether this was a good idea to stop, because although you are going slow, because at some point in double precision minus 16 will be anyway, like below this may not be reliable anyway, right? So you may stop at some point. Below that you may not trust, right? So you may say that maybe I'm not progressing, maybe it's an indication that the gradient is becoming flat, and then I should stop. But who knows, it was still decreasing, maybe it became a bit slow, and then it could have gone like this. So maybe you stopped here, but ideally you should have gone even further. Okay, and your dual gap was still very large. Okay, although you don't know P star, but it could happen that the minima was somewhere here, and you thought that the difference of these xk plus 1 and xk here, xk plus 1 and xk are these values are not changing. So you are assuming that maybe you are already to optimal. But having a knowledge of the dual can help you with the direct estimate. Of course, again, lambda nu is what you don't know. You have to guess. But but it is giving you some kind of a proof or certificate in some sense of where you could be, although you don't have a very good estimate of lambda nu maybe, but it's still giving you some upper bound on the actual difference of the function value with the optimal value. So that's why this can be useful, provided that you can formulate the dual function and then test with some lambda nu, just to keep a check of how. I mean, this is very useful when some test value that you have provided, it's already difference is already like which can be computed. So it's already 10 to the minus 10. Then you can say that I'm surely less than 10 to the minus 10. Okay, so I'm so close to the primal. So this can be used, but there are slightly better ways of doing this upper bound. Okay, so we will see this later. Okay, so the duality gap associated with x and lambda x can be defined like this. So what is the difference between? So this is the duality gap with primal x and dual variable. Okay. So one duality gap we know is like d star, P star minus d star. But here we are talking about duality gap associated with the variable, then we take this difference. So this is the duality gap associated with the variables. So certificates for primal and dual. If the duality gap corresponding to the primal dual feasible pair and lambda nu is 0, then in that case, obviously this is equal. And then we claim that x is primal optimal and this is dual. And here lambda nu is the certificate that proves that x is primal optimal, and x is a certificate on the other hand. Other way, x is a certificate that proves that lambda nu is dual optimal. So they can act as a certificate of each other. Okay, so non-heuristic stopping criteria. If an algorithm produces a sequence of primal xk and sequence of dual, so if you happen to have an algorithm that also produces a sequence of dual, then this can be used as a stopping criteria. Okay, of course, you have your algorithm should also run algorithm for the dual. Okay, so this is algorithm for the primal and this is algorithm for the dual, and then you can keep doing these checks, assuming that your g is increasing. Okay, so your f xk are coming from this way, and g lambda k nu k are coming from this way, and somewhere there is a optimal here. Let us say it's p star. If the strong duality holds, then d star will be also overlap. So you can like use it as a measure to know how close you are. If you are very close, then obviously the difference of this will be less than some epsilon small value. Okay, so that can be used, provided you can run also a dual algorithm to generate lambda k and nu k. Okay, so there is something called, I'm now going into something called primal dual formulation. So primal dual. So what we have seen so far is that I can write the optimization problem as a primal problem, or I can write optimization problem as a dual problem, right? So we have seen two different ways, but there is a intermediate way where I can have both primal dual both simultaneously, and then I have to solve simultaneous set of problems. So let us go towards that. So to go towards that, we need a few additional steps. First step is so-called complementary slackness. Suppose x star is a primal optimal, and let us say this is the dual optimal in our usual notation of superscript. Then let us say we start with f naught x star. So this is the objective function, and then we put the primal optimal value here. Okay. So this will be equal to g of g of lambda star and then nu star. Okay, and then I can write this as infimum over x. So this is the definition of the g, and then this is the Lagrangian. Okay, so f naught x plus this and so on. So now I have put this x here, right? Okay, and then lambda star nu star is lambda star nu star here. Okay, and there should not be x star here. Okay, this is just x. Okay. Okay, so this is infimum over x. So this must be less than equal to, if I put some value of x here, then that can be greater than equal to this, because this is infimum. So if I put some x star here in place of x, then that will lead to greater than or equal. Okay, so I put a x star here, and x star here, and x star here. Now, now why it, so what I'm claiming here is that this will be less than equal to f naught x star. Why is that? Because lambda is are greater than equal to 0, and this is the constraint. So this is like less than equal to 0, fi x star. So overall this is like less than equal to 0. And these are equality constraint anyway. So this is equal to 0. So it doesn't matter what this guy is. So we can also take this as less than equal to 0. It doesn't matter. It is equal to 0 anyway, right? Because hi x star is equal to 0. So in that case, so this guys is like less than equal to 0. This guy is less than equal to 0. So overall, this must be less than equal to f naught x star. Okay. Now, what do we get? F naught x star less than equal to f naught x star. Right. So what I'm trying to say is 2 is less than equal to x is less than equal to 2. This implies x must be equal to 2. Right. So the intermediate inequalities must be equality. Right. So that's what it proves. Right. So intermediate inequality that we wrote, it must be equality. The inequality in the third line must be equality. Okay. So in other words, what does it say? So in other words, this says that x star minimizes the Lagrangian. Okay, because this is forced to be an equality now. So this is forced to be an equality. This means that the infimum is achieved at x star. Okay, that's what it means, because the infimum of this is equal to this for x star, then it means that x star has solved this infimum problem. And if that is the case, then it also tells us that x star is a minimizer of the Lagrangian, right? Okay. And the second one is, so what does it, yeah, so and the second one, so here, like here this was equal, right? And here this is equal to 0 anyway. So what does it prove? Right, if this is an equality, right? So this guy is equal to this guy, right? So this means that these guys must be 0. Okay, or so I mean, yeah, so this is already 0. So for the equality to happen, this guy must be forced to be 0, right? So this guy must be 0. So if this guy is 0, okay, because the fourth inequality must be equality, because all intermediate inequality must be equality, because you started with and you ended up with this guy. So any inequality that you have, so this will also be an equality. So this forces this guy to be equal to 0. Okay, it cannot be less than 0, otherwise it will force strict inequality. So this must be equal to 0. So this forces us to have this. And this is called complementary slackness. Okay, so if the duality gap is 0, or in other words, the strong duality holds for a problem, then this condition holds, and this is called complementary slackness. Okay, complementary slackness. Okay, so that's something we know. For strong duality, this is what we have. Okay, so now we can wrap up, we can put all the knowledge we have into so-called Kkt conditions. Okay, so the usual definitions hold. So let us assume that F0, F1, Fm, H1, Hp are differentiable, because we are going to use that in the Lagrangian, right? So and we have like no assumptions on convexity. Okay, so that's important. And so that's first. Second is let X star and lambda star nu star be the primal and dual optimal with zero duality gap. So Kkt conditions we form when we assume zero duality gap. Okay, so that's the given thing. Now, since X star minimizes the Lagrangian, we must have this. So the gradient of L, because X star is a minimizer, so it's a critical point. So critical point, the gradient must vanish. So this is the so gradient. So this is like grad L X star lambda star nu star is this, and this must vanish because X star is the minimizer. So Kkt conditions is a collection of all the things that we have seen. So these are the inequality constraints. These are the equality constraints. So these are coming from the problem itself. Okay, nothing. This is also coming from the problem itself, because the inequality parameters are assumed to be positive, non-negative. So this is also given. And this is the complementary slackness that we have just proved, okay, in the previous slide. So this is complementary slackness. And this is what we have here. Okay, so this is this condition here that we also put it here. Okay, so what we see, this list of conditions we have is the so-called Kkt conditions. Okay, so these are like a name of the people, okay, who came up with this. Okay, so Kun, Tucker, and then there is one something like Carl or something. Okay, so they're like, I mean, there one of the guy was like MS student actually. So he discovered this independently, and Khan Tucker were like more older guys. So the first K was like MS thesis, 20 something year old. Okay, so he defined this. He came up with this independently. So that together, both the groups did this independently. So it's named after 3 people. Okay, so this is like a thesis work. Okay, to come up with these conditions. Okay. Yeah, not that difficult if someone tells you, but if you have to invent things on your own, then it requires some effort. Okay. Okay. So this is so-called Kkt. So now let us. So Kkt condition for the convex problem can be do something better, because so far we have not assumed any convexity. So Kkt can be written in general like this. If it is a convex, then when the primal problem is convex, then Kkt conditions are also sufficient, okay, for the points to be primal and dual optimal. Okay. So what are the changes we have here, right, compared to this? So they are like also sufficient. So what it is trying to say is like we don't additionally need to assume zero duality gap that we need in the Kkt condition. Okay, so what this is trying to say is like if your problem is given to be convex, then the Kkt conditions are also sufficient to imply strong duality. Okay, so this means sufficient to imply strong duality. Okay, so you don't need to do this additional assumption, okay, for the convex case. So that's what it's trying to say. There is a proof of this. I think I'm going to skip that. Okay. So Okay, so we have like an example also here. Like we can try to write Kkt conditions for this example. So what are the Kkt conditions for this? Okay, so we can try to write down, right? So in the Kkt conditions, well, it is given that it's positive definite, and this is this is a convex optimization problem, convex problem. So we can so what we are sure about. So this implies strong Kkt will imply strong duality. Okay, this is from the previous result. So we are not worried about that now. So Kkt does imply strong duality. So if we write down the Kkt condition for this, right? So what are the things we need? Inequality constraint. Well, we don't have inequality constraint here, so nothing to do here. Equality constraint, yes. So we have equality constraint. So we just write down the equality constraint, Ax equals to b. And then lambda I is greater than, well, lambda I goes with inequality, but inequality we don't have. So this is we don't have. And this also we don't have because lambda I with the inequality, right? So this also we don't consider. Now we are left with is this. So f naught x plus mu times. So let us write down the Lagrangian. Okay, so this is the Lagrangian, and we have to take the gradient of that and equate it to 0, right? You have to take the gradient of that and equate it to 0. So gradient of L of x nu. So this is the gradient of this with respect to x, right? So this is with respect to x. So this is px, and then plus q, px plus q, and then plus nu. Yeah, and we are taking gradient with respect to x, right? So this will be yeah, A transpose nu, right? A transpose nu, that's it. The other guy will be 0. Okay, so this will be, so the Kkt condition will be like this is also equal to 0, right? So this thing was there in the Kkt in our problem, and this was there, and boom. So what do we have? So we have this simultaneous set of equations, right? So Ax equals to b, and px plus q plus A transpose nu is equal to 0. Okay. So now what do we do here? Well, this q I can move it here, right? So let me do that. Okay, so and then can I write this in a matrix form, right? Because these are not just matrices, right? So here I can write x a 0 p A transpose x nu is equal to b minus q. Okay, so this boils down to this: Ax equals to b and px plus A transpose nu equal to minus q. So this is a linear system to solve. Okay, so you can use linear algebra. This is a problem where you can see both, right? So both primal and dual are there, but what you will report to the person who has given you the problem is just the primal, because that's what was needed anyway. Okay, but you are also getting the dual. Okay, so you are getting both primal and dual simultaneously. Okay, so 1 plus 1 offer. Okay. Okay. So solving the primal problem via the dual, right? So earlier I told you that you may end up solving your dual problem and to obtain lambda star nu star, but originally the person needs, but we need x star. Okay, the primal optimal we need. So what do you do? Well, let us say that you don't do Kkt. Let us say you do go for the pure dual problem, and you solve for this, and you get lambda star nu star. Okay, and then how do you get to this, right? How do you get to this? So this is what it's trying to explain. So suppose the strong duality hold. Obviously, strong duality should hold because then only I can hope for getting to X star. I mean exactly. Otherwise, we will just approximate it, right? So suppose the dual problem is solved and dual optimal is known. Moreover, suppose the minimizer of this exists. In other words, so what we are supposed to do? Well, we are supposed to like minimize this. Okay, and the place where the minima will exist for this, okay, that will be my primal optimal. Okay, so the steps involved are form a dual problem, and then obtain dual optimal parameters. So optimal parameters which are lambda star and nu star, and then to get the primal optimal, solve this. So to get primal optimal X star, you have to solve another minimization problem now, but apparently this may be easy enough. Okay, so because there are no constraint anything, right? So okay, I mean there is a minor constraint here, lambda I are greater than equal to 0, right? Okay, so you have to solve for this, minimize f naught x plus this lambda I fi plus mu I hi. Okay, so you're supposed to solve this. So the minimizer x that you will get here, that will be your X star. Okay, so this is how you will report X star. After you solve the primal, you have to solve one more optimization problem. Okay, and then that will be your X star. So I think I have some time. Yeah, I have half an hour. So now what I will do is that's the end of duality. What I will do is that I will go to some optimization models in the next few classes and tell you how in applied domain how optimization problem appears. Mostly, let us say in data science or mostly data science problems. So let us see so-called recommender system. So in recommender system, you are given a history of movie ratings. Okay, so it's given by the user, and based on that, I may want to recommend suitable movie to some other user. Okay, so let us say we have a list of movies here, and then let us say the user gives ratings. Okay, so here let us say Anna gives rating 4 actually, right? So this is 4 here. Okay, so there are like 4 users and then 5 movies, right? So these are like movies and these are the users. And let us say one person gives a rating 4 to the movie 5. Similarly, all other users will give rating for the movies. So let us say they give ratings like this so all the users have given ratings to all the movies they have watched. Okay, when all users give the rating for all the movies, and let us say these are some of the examples of the ratings that they found. Okay, that the users gave. So which of this you think is more realistic movie rating, right? So because here I see all are 3, right? So it looks not very realistic because it's very rare that all people all will give the same 3 rating, right? It's very unrealistic, right? The first one does not look realistic. Okay, very rare that the user will give same rating to all the movies. The rightmost one also does not look realistic. Why? So why rightmost one is not very realistic? Why is that? It's like 1 3 2 5 4 and then 2 1 1 1 5 3 2. What is going on here? Column wise, so 1 2 3 2 and 3 1 2 4 2 1 3 1 and 5 1 1 5. Okay, and then 4 5 5 2. Okay, so what is not very realistic here, right? That's what we are trying to see. So let us say it's a movie. Movie 1 is 1, 2, 3, 1, 5, and 5, 5. Okay. What is not realistic? When there are many movies and many users, it's rare that all will give different ratings. Okay. So the okay, I see. So the unrealistic thing here is that it's very rare that all will give different ratings to a movie. Okay, for example, this guy gave rating 2 and 1 here, 1 here. So it's very rare that they are matching. They are matching, but it's very rare. That's what it's trying to say. Okay, so it's very rare. So this person is giving 3, 1, 2, 4. Okay, so they are matching only here and here, and then they are matching only here and here. Okay, so this is like also unrealistic because in general there may be more overlap. Okay, for example, here in this case user 1 gave the rating 1 also, and user 3 also gave rating 1, but they also matched here, where they have a rating 1 and 1, and they are also matching here. Okay, in fact they are matching in this case as well. Okay, so so what is more realistic is that we expect some overlap, especially if it is large. Okay, if there are many movies and many users, that's the key thing here. Many movies and many users, then we expect a lot of overlap or dependencies. Okay. Okay, so what does this have to do, right? So let us think about dependencies now. So what are the dependencies in this? So these arrows tell you what are the dependencies, right? Well, dependency is like 3, 1, 1, 3, 1, and here also 3, 1, 3, 1. So, well, they are exactly the same. So the third row is 1 times the first row. That's the dependency, right? Or they are exactly the same. Can we spot the dependency here? What do we see? Well, they are also same. So the first column is same as the fourth column. Okay, so they are dependent. Okay, so they are dependent. Okay, so but does this imply that the movie M1 and movie M4 are same? Okay, so does this imply that because movie M1, all of them because the ratings are matching, right? For all the users, the ratings are matching for movie M1 and M4. Then the question is like, does this imply the movie M1 and M4 are same? Right? So, well, it may not be same, okay? But what it does imply is that many of the features of these movies may be actually same. Okay, so maybe the action here and then maybe the amount of action here and the amount of action here is the same. Okay, so maybe like some some other features movie may have like comedy. So maybe the amount of comedy here and here may be the same. That is why this user is giving 1 weight. Maybe let us say same amount of like things are like matching. Okay, so the features may be matching. Okay, so that may be the reason to explain this. So well, not the same, but maybe similar. That's the idea. So can we find more dependencies? Let us look into this 3 pointed arrows here. So here, do we see some more dependencies? Well, we see that the last row is a sum of the second and third row. Okay, so R4, the row 4 is equal to row 2 plus row 3, right? So this is also a kind of dependency, right? If you see in terms of matrices, then this is a dependency. So okay, and similarly we can ask in terms of column, right? So column 5 is an average of column 2 and 3. So column 5 is average. So 5 plus 3 by 2 is 4. 2 divided by 2 is this, and 6 divided by 2 is 3, and 1 plus 1. Okay, so this is also giving us some average. So what could be the meaning of this, right? The meaning could be like the movie M5 is an average of the movie M2 and M3. What average we don't know. Maybe it's the average of some features, average of the actions, average of the comedy part, and so on. Okay, so this is what we are intuitively trying to see here. So in other words, if M2 is a tornado movie and M3 is a shark movie, okay, so this is, let us say, tornado movie. So the Twister movie that you may have seen, and then there is a shark movie which is Jaws. So it may happen that this Sarknendo movie. Okay, so this movie combines both Tornado and Sark. So maybe this is an average of this. Okay, and that's why the ratings were came out to be average of that. Okay, so it may happen. Okay, so one more thing is like it may happen that some user have watched and given ratings to all, but it may happen that one of the user has not watched M4 at all. Okay, and we are interested in recommending this to this user. Okay, based on what other users have done. Okay, based on what other users have given the ratings. So what we see from here is that the ratings given by all the other people are exactly matching. Okay, so again, one thing is like such rating metrics may be very unrealistic, but just for an example, all other places are 3. So it seems that the movie recommendation that we are going to do this for the user 3, the recommendation of M4 movie will be 3 itself. Because by looking at the pattern at the other places, we believe that user 3 will also, it's a prediction problem now. Okay, we don't have to be very precise. But what we are predicting with high accuracy is like it is going to be 3 rated as well. Okay, and how we do that? Because we are also looking at the pattern of the other users. Now look at the rating matrix, and dependencies predict the rating 3, and we recommend 3. Okay, so which rating to predict for user 3 for movie 5? So let us see this. You are given a task to recommend to predict for user 3 for movie 5. Now looking at this ratings matrix so far, the incomplete rating matrix, what are you going to suggest for user 3? So what should I fill here? Right? What do you think I should fill here?
It should be 1.
It should be 1. Why?
Same as the first user.
It is same as the first user. Yes. So if we look at the user 1 and user, so they are matching at these places, these places, these places, these places. Okay, they are matching. So it seems like looking at that pattern, it should also be 1. Okay. So we are going to recommend 1. Okay. So and then let us look at yeah. So they have both the rating. So it's the solution to that. So they both have the same rating. So we are also going to predict the rating 1. Okay. Okay. So the game here is now to identify the dependencies. Okay. So it's more like a linear algebra problem actually. Okay. And why is that? What we are thinking of is that these rating matrices are kind of a product of 2 matrices, and if I multiply this with that, then I get something like a rating matrix. So what we are looking for is some compact representation. Okay, so maybe it's not very clear what I said. So let us see in detail. Okay, so what we see is that if the matrix do have dependency, then it's a low rank. Right, so it's a low rank. If it has a dependency, then it's a low rank. In other words, the easiest possible case would be, let us say 1 2, okay, and then 1 2. So 1 2 and then 1 2. So if I multiply this out, then this will be 2 by 2 matrix, right? So this will be 1 and then 2 and then 2 and then 4, right? So this is a 2 by 2 matrix. And I could write this as a product of vectors, right? So I could write this as a product of vector, and then I get a 2 by 2 matrix. So I could see this matrix as a low rank, because this is low rank. This is rank 1. This is rank 1. So I could multiply rank 1 to get a matrix. Obviously, this is also rank 1 only because, okay. So, and it is clear because the first row is just a multiple of the second row. So this is indeed a rank 1. So given a very large matrix, our problem is a reverse one. So given a large matrix, can we write this into a low rank form? Because if there are dependencies, then it is possible. So I told you this way But if this is the case, I must be able to write it in this form. Okay, both ways is possible. Okay, so I should be able to factor. So now the problem reduces to now finding the dependencies is like finding a low rank factorization of the ratings matrix. Okay, that's how I see this problem. Okay, so if the matrix has rank R, then it can be written as a product of rank R matrices. Okay, that's the hint I gave you. So how to do the matrix factorization, right? So what is the intuition behind all this, right? So let us see this. So if I say that I am going to do this into a low rank, what I'm trying to do implicitly is like I'm trying to extract the useful features of a matrix. Okay, useful features, and those useful features are enough because the movies will be, let us say, by now there will be billions of movies, right? If we take all those movies in all the languages, right? So many movies are there, and people like movies based on certain features. Okay, although movies may be all different, but there are features that attract the people to movies. So low rank, finding a low rank is like extracting some useful features of features. In this case, it could be comedy, action, drama, whatever. Okay, so intuitively, this is what it means. So in other words, let us say movies may have certain features like comedy, drama, and action. Okay, so the movie may have certain prominent features, and these are the latent features. Okay, the latent features are the features that are hidden, that were not told to me in the data explicitly. In the matrix, no one told me which was adventure movie, which was. I'm not assuming any of these things. Okay, someone just gave me ratings matrix, and I have to identify from there itself. No one told me this was a shark movie, this was a tornado movie. No one told me that. Okay, that's not part of the given data. Okay, so but we still want to figure out some these features, but we want to figure out this in these hidden features, which was not told to me. So that becomes hidden feature. Anything hidden, we call it latent in machine learning language. Okay, so we talk about, so these are latent features. These are hidden features in the ratings matrix because I was not told about the movie. Okay, these are just data to me. Okay, so these ratings metrics do not tell explicitly about these features. The most movies may be characterized into selected features. So this is something we know, that we do characterize things like that. Okay, so one could be comedy, drama, or action. But this is something we categorize from our view. But from linear algebra point of view, it will be the rank that will determine what are those features. So those useful rank will be preserved, and they will correspond to the features. Okay, so that's hidden thing that will be done by linear algebra itself. Okay, so to see an example, let there be two features, and let us say comedy and action, right? So let us say Anna likes comedy, but she hates action. Okay, and let us say I'm assuming right now. Okay, I did not say that someone told me this, but I'm assuming that, let us say this movie Mali Cop, okay, has three parts comedy, three parts of this is comedy, and one part of this is action. Let us say that. Okay, although in a general case it won't be given to me, but this is for this example. Let us assume that this is three part, this is one part. Now you can see what C is going to give the rating based on this feature of this. So C likes comedy, so it will be like, okay, so C will say, okay, I like comedy, so it's 1 times 3. C doesn't like action at all, so this is like 0 times 1. Okay, so it is expected that C will give rating like this, expected. Okay, because C likes comedy so much and it has so much comedy, she will like it and she will give higher rating. Okay, so that's how we figure out the relationship between these features and then what C is going to predict. Okay, so C is going to do the 3. Okay, so that's what I calculated. Now Betty C is going to C likes action more than comedy. So if for her case it will be 0 times 3 plus 1 times 1. So this is it seems that she is going to predict 1. Okay, for this movie. Okay, so if we can write this in a tabular form, assuming that that the features are identified. Let us say we are restricted to 2 features only, like comedy and action for the moment. Okay. In general, there can be more. And this actually corresponds to the rank. Okay. So it will be related to that. And again, these are the features. So the movie have these features and the users also have a preference for the features. So she likes comedy, doesn't like action. She doesn't like comedy. She likes action. He doesn't he likes comedy and doesn't like action, and then he likes comedy and action as well. Okay. And then the movies also have these features. So movie 1 has 3-part comedy, 1 part action, 1 part comedy, 2 parts action, and so on. So based on this tabular data, now one can predict. Obviously, we don't know this, and obviously we also don't know this. That's the tricky part, right? We neither know this table and we neither know this table. If we knew, we can do the prediction, right? So that was okay. But we don't know this. The user did not tell me which part they like, which part they don't like. And the data given rating data also did not tell me which movie has which part comedy, which part action. That's the tough part, right? But if it is known in this example, right? If it is known, then this is how we believe the rating is going to come out. So these are the examples of the ratings I'm just. So, and this is how we can fill out the ratings matrix if we knew something about the movie feature matrix and the user feature matrix, and hence we will get the ratings matrix. Okay. So this is somewhat related now to matrix factorization, right? Because this matrix, I could see this as this matrix product, right? So how did we do the product, right? So you can see this as a product, right? So let us fill this as 1 0 0 1 1 0 and 1 1, right? So this is the user feature matrix. User feature matrix. Okay, and this data is already given to you. This is the movie feature matrix. So now what do you do, right? So how can I multiply this to get this, right? So I can multiply these, right? So what I'm supposed to do, this times this and this times this, right? So one, I have to do a transpose, right? So if I do a so this and then this transpose, okay? So it's like 3 1 1 2 1 4 3 1 1 3, and then this. You see, low rank are always like this. One is taller and other one is less taller, right? So this is like and transpose of this, right? So this is like 1 0 0 1 1 0 1 1. Okay. Now if I multiply this, then 3 times 1 1 times 0. This is the rating for this guy, and 3 times 0 1 times 1. This is the rating for this, and so on. So this is the low rank factorization, right? Here is the low rank factorization that we did to obtain the ratings matrix, right? Or you can reverse this problem now. You went from here to here. Now what you are given is a ratings matrix is given. Can you do this? So it's a low rank factorization problem. Okay, given a matrix A, can I write this as U V transpose, where U and V are low rank, right? But there is a further complication here. The further complication here is some part of the matrices will be missing for you, because that's the part of recommendation. Because everything was filled, then everything is recommended already, right? What is interesting is like when some part of the data is missing, and that we are supposed to predict, right? And if some part is missing, then how will you do the low rank factorization anyway, right? So there is still some tricky part here. So what we observed so far is that low rank factorization is this. So we can do this as low rank factorizations, and then if there is a dependency, then these dependencies are preserved. You can always check that, okay? And this explains why the rating matrix will have the same rows. So these dependencies will be preserved by the nature of, because it's equality, right? U V transpose is equal to A. So the dependencies are supposed to be preserved, right? So dependencies this and this are preserved because they were same. They are going to produce the same rows eventually. Okay, but in general, if you think about, I am going to stop now. So in general, if you think about a very big matrix, let us say 2 million entries, then computing this low rank is I mean, first of all, like you cannot store this because this is like too many. Okay, so matrix factorization has benefit in the sense that it can be compactly stored. Okay, so this is my original data, but then I can factor this into two smaller because many dependencies are expected. So I can store this compactly into just two matrices. Okay, so that's the first advantage in terms of storage. So it's enough to store only feature metrics and so on. We can also see this in terms of graph. Rather than mapping a user directly to the movie, what we are trying to do is a low rank factorization. We are mapping them to a selected set of features. In this case, it's like comedy and then. And similarly, we have user feature relationship and we have feature and movie relationship. Okay, and that's how like we can compress this. This network has a lot of storage requirement, but this has much lesser. Okay. Okay, so I think we will stop here and we will continue with this. Our goal is to write this as an optimization problem. Okay, so we will see various applications and we will try to write these many problems as optimization problem. Okay, and then at some stage I will show you more algorithms. Okay, to solve. Okay, so we will stop here.
Sir,
Yeah.
sir, actually, I want to ask some questions. Means like how many